All right, welcome y'all. This is the practice test. I'm going to go through it pretty quickly, as clearly and concisely as I can. Starting with number one, which is a correct statement for the reaction below? And we have this nice redox reaction with permanganate and nitrite ions. So what we're going to do is we want to find out which is a reducing and oxidizing agent, as well as what the oxidation state of these are. I like to just go left to right. So I'm going to start with manganese. So Mn goes from a 7 plus, and it goes all the way to a Mn2 plus. If we remember oil rig, oxidation is loss, reduction is gain. We can see that manganese is actually going from a 7 plus to a 2 plus, which means it's being reduced. It is gaining electrons, therefore it is being reduced. So right now, this tells us that theoretically, B could be the right answer. And if B is the right answer, where manganese is decreasing in electrons, D could also be the right answer, where nitrogen is increasing, because it would be doing the opposite. Now, they both mention oxidizing agent, but remember, the oxidizing agent is also the thing that is being reduced. If it is being reduced, then it is acting as an oxidizer. We know this answer is B. So, number two. For number two, what is the order of decreasing reactivity of the metal? So basically, if the solid reacts with the solution, we know that the solid is more reactive. So from this first one, we can tell that zinc is more reactive than tin. From the second one, we can tell that zinc is more reactive than copper, because zinc not react. The third one, we can tell that tin is more reactive than copper. And from the last one, we can tell that silver is less reactive than copper. So we can see from all of these that copper is not very reactive, but silver is even less reactive. So we know that our ending elements are going to be Cu, Ag. Because of that, I already know that the answer is going to be D. And then I know that tin is more reactive than copper, so Sn. And I know that zinc is more reactive than tin, Zn. All right. What is the oxidation half equation in the redox reaction? So oxidation half equation, we are looking for something specifically that is going to increase in oxidation state, something that is not being reduced. So again, I'll just start from the beginning. S2O3, 2 minus, and I don't really care about the coefficient. I know that each oxygen is going to be producing a 2 minus charge, so that is 6 minus. But really, because of this 2 minus, it's acting more like a 4 minus for this to split. So sulfur individually is going to start at 2 plus. 2 plus would be 4, 6, 4 plus, 6 minus. That would create our 2 minus charge. Cool. Moving on, sulfur in S4, O6, 2 minus. So for this one, we are going to see that, again, we have that 2 minus. So these 6 are going to make a 12 minus charge. Really, it's acting like 10 minus. 10 minus being balanced out by 4. Each sulfur is going to be 2.5 plus. And we can have this half oxidation state, because really these are all charges being shared. But we can see that sulfur is being oxidized. So the half reaction that we're looking at is going to be the one that has sulfur being oxidized. So that brings us to one of these two. Now we just have to make sure that our charges are balanced. 2 and 2 minus is 4 minus. 2 minus 2 minus is 4 minus. Our answer C. It cannot be D, because D doesn't even have D is the backwards version of C, which honestly makes no sense, because again, we're looking at the forward reaction. So our products and reactants must remain our products and reactants. Moving on to number 4. This one, we just have to look at increasing activity. Which of the following would not react with HCl? Well, H is a reactive thing, so it's anything below H in reactivity. It's going to be copper. So the question you might ask is, why not copper oxide? Well, in copper oxide, copper already has Cu2 plus oxidation state, and so it's not going to react in this form with H plus. There's nowhere for that charge to, or that absence of charge to go. H plus is trying to gain electrons, but regardless, in that Cu2 plus, it can gain electrons from oxygen maybe. So copper oxide are going to react differently than copper itself. So for this one, our answer is in fact B. Moving on to 5, which element is reduced in the following decomposition reaction? So for this one, again, I just like to go from left to right. We're going to start with nitrogen. Nitrogen in ammonium, NH4 plus, nitrogen will have a 3 minus charge. Nitrogen in N2 is going to have a 0 charge. So turns out it is going to be losing electrons. If it's losing, it's being oxidized. So this is an oxidation. So not nitrogen. All right. The next big suspect is going to be chromium. We almost never look at hydrogen or oxygen in these because we're usually doing these in acidic environments. So moving on to chromium, Cr is going to start with a 7 plus and Cr2O7 minus, or 2 minus. So it's going to be a 7 plus. It is then going to go and become a Cr3 plus and Cr2O3. So therefore, this one is being reduced. So it's chromium. All right, which of the following is not a redox reaction? Basically, you just want to check your oxidation states here. We see chlorine's going from a 0 to a -1. That's an oxidation happening. Oxygen's going from a 0 to a, or sorry, that one, first one was reduction. But oxygen's going from 0 to 2 minus, again, reduction. Here in carbon monoxide to carbon dioxide, or even just a carbon is going from 2 plus to 4 plus. Again, change in oxidation number. So by default, it's got to be D. The other thing is D is just a basic acid-base reaction, exchanging of protons, but no actual change in oxidation state. Moving on to number 7. Which change represents oxidation? So again, we want our oxidation number to increase, not decrease. So for this one, starting with number 1, we see right here, chlorine is going to go from a 7 plus to a 5 plus. That's a reduction. Nitrogen is going to go from 0 to 3 minus. Again, that's reduction. Nitrogen is going to go from a +1 to a +2. Oh, hey, look at that, oxidation. Answer C. All right, moving on to number 8. A reaction takes place when a rechargeable battery is used. Lead plus lead oxide reacts with hydrogen ions and sulfate to react to lead sulfate and water. Which statements are correct? H plus is reduced. Okay, so first off, it's almost never going to be H plus being reduced. H plus being reduced is just going to turn into H, but hydrogen always is going to act as positive. It's not going to be 1. We can even check. Hydrogen goes from a +1 to, oh, look at that, a +1. No reduction. Oxidation state of PB metal changes from 0 to +2. It is 0. And when we come here, oh, look at that, it's +2. And we know that because the sulfate ion, SO4, has a 2 minus charge. So regardless of what's happening with the sulfur, whether or not it is oxidized or reduced, the lead is going from 0 to +2. That is correct. PbO2 is the oxidizing agent. So we can honestly just look at our original one of Pb right here. So Pb is going from 0 to +2. It's being oxidized. Therefore, it's the reducing agent. Therefore, if it's a reducing agent, the other thing must be the oxidizing agent. So I'm going to say that is the correct answer. So C, 2 and 3. Which element is reduced in the following decomposition? All right, so for this one, once again, we have to go through and figure out what is actually happening. But we did kind of already look at this one before. Nitrogen's going from a 3- to a 0. To me, that looks like an oxidation. Cr 2+ is going from a 7+ to a 3+. Oh, look at that. That's reduction. Cr. That's exactly what we said earlier. Which statement's being reduced? Oh, actually, I had the same problem twice. Hopefully you got them both right. Did not even realize. Freebie points. Moving on to number 10. Which compounds can be reduced? So for these, you just want to look at each individual ion, whether or not they have the ability to either gain or lose electrons. Starting with the first one, C2H4, each carbon here is acting as just a 2- to balance out the 4 hydrogens. We know that carbon in CH4 can act as a 4-, so it can definitely be reduced. The same thing is happening with this carbon in C double bond O, OH with another C. We can break those bonds. We can maybe add another oxygen. We could have OH, OH. That would oxidize it, or we can surround it by hydrogens, and that would reduce it as well. And same thing with this carbon right here. Again, we can just surround it by hydrogens. It's D, 1, 2, and 3. So just to clarify this one a little bit more, in this case right here, the carbon is taking a -1 from this oxygen, a -1 from this oxygen, a -1 from that oxygen. Therefore, the carbon is acting almost like 3+. However, if carbon and methane can act as a 4-, we can definitely reduce carbon. So that is that answer. Moving on to our massive paper 2 question. All right, when heated in air, magnesium ribbon reacts with oxygen to form magnesium oxide. Write a balanced equation. All right, Mg solid plus O2 gas reacts to form MgO. Quick balance, we put a 2 here and a 2 there, done. Take the block of the periodic table where magnesium is located, S block. When you look at your periodic table, really bad drawing, S, D, P, F. Magnesium's right here, S block. Identify a metal in the same period as magnesium that does not form a basic oxide. If we're looking at our periodic table, periods are the ones that go across. Well, we have only sodium, magnesium, or all the way over here, aluminum. Those are the only metals that we're actually looking at. We know sodium can form an oxide, magnesium can form an oxide. It's actually aluminum, does not form a basic oxide. It kind of acts weird like a metalloid in those cases. You can just kind of guess that because it's really far away from the other metals. And periodic table, we know that the arrangement helps us determine properties. So things that are closer together probably have similar properties than things that are far away. All right. The reaction was carried out in a crucible with a lid, following data recorded. So calculate the amount of magnesium in mole that was used. Well, we can just do 53.726 minus 47.372, and we will get an answer of 6.354 grams mg. Do a little bit of stoichiometry. We have 24.31 grams mg, 1 mole mg, and turns out we'll get an answer of 0.2614 mole magnesium. That'll get you your credit. Determine the percent uncertainty of the mass product after heating. This one's a little bit more difficult, but uncertainty of the mass of the product. So we need the mass of the product. And to get that, we will just take our original mass, our mass of the product minus our original mass of the crucible. So we're going to do 6.941 minus 47.372. That will get us 9.569 grams. That is our mass of the product. Our uncertainty is this 0.001 grams plus or minus, which means we could be 0.001 over or 0.001 under. So our actual uncertainty is 0.002 grams, because once again, we could be 0.001 over or under, which is a range of 0.002. And we'll divide that by 9.569. And that's going to get our percent uncertainty or percent error. That's going to get us 0.02%. It's really 0.0002. And then to turn into a percent, we just do a quick little times 100. Whoops. Let me just put that back to normal. Times 100 to get a percentage. All right. Assuming the reaction is the only one occurring and it goes to completion, but some product has been lost from the crucible, determine the percent yield of magnesium oxide. Well, to determine the percent yield, we first need to find out what our theoretical amount would be, our theoretical yield should be. So we will take our original 0.2614 mole mg, convert 2 mole mg to 2 mole MgO using our balanced chemical equation. Then we will use 1 mole MgO with 40.31 grams MgO. So this is just stoichiometry, cancel our units. And we get an answer of 10.536 grams MgO. That is our theoretical yield. But here's the problem. That's not our percent yield. Our percent yield is going to take our theoretical and use that to be divided by our actual. Now, our actual yield we found out before by taking our product minus the original mass of the crucible. So we're going to take 9.569, divide that by 10.536, and we're going to get approximately 91% yield. Again, we're multiplying by 100 to get that. All right. Moving on to our next problem. When magnesium is burnt in air, some of it reacts with nitrogen to form magnesium nitride according to the equation. Evaluate whether this, rather than the loss of the product, could explain the yield found in part 3. So when I look at this, I try and see, well, we have a reduction in mass. Would producing magnesium nitride also cause a reduction in mass than what we should normally get? If so, then recording a reduction in mass would also likely be due to magnesium nitride. So I'm going to actually do the exact same stoichiometry I did before of 0.2614, 0.2614, and again, mole mg, and do this time 3 mole to 1 mole, mg3 and 2, mg3 and 2. Oh, whoops. Just mg. Then multiply by the mass of mg3 and 2, which is 114.96 and 1 mole. And we get an answer of 10.07 grams mg3 and 2. This is notably less than if we were to produce MgO. We have 10.536 versus 10.07. So by producing magnesium nitride, we are still producing less. So we wouldn't say this would explain all the loss of the product, because all the loss of the product should be somewhere around 9.56. But yes, this can cause a decrease in mass of product. And furthermore, we are actually using more magnesium to produce magnesium nitride. So every magnesium we use to make magnesium nitride would actually cause less magnesium oxide to be produced, which would further decrease the mass. So suggest an explanation other than product being lost in the crucible or reaction with nitrogen that could explain the yield. Well, there's a lot of reasons. Some could be impurities in the magnesium ribbon. Others could just be the ribbon was already oxidized. There are many, many reasons for it. There are a lot of different variations. We could have incomplete combustion, incomplete reaction. Many reasons. All right. Next is balancing the coefficient. Well, to get 3 magnesiums, I'll just multiply by 3. To get 2 nitrogens, I'll just multiply by 2, which is going to produce 12 hydrogens on this side, 6 oxygens on this side. So I'll go ahead and do 6H2O, 1, 6, 3, 2. All right, determine the oxidation states of nitrogen in both of these compounds. Well, Mg is 2 plus, and we have 3 of them, so that's 6 plus. Therefore, divide by 2, that is 3 minus to balance out from the nitrogen. So 3 minus. NH3, again, 3 plus from the hydrogen, therefore 3 minus from the nitrogen. All right, no change in oxidation state. So moving on to D, part 3, deduce giving reasons whether the reaction with water is acid-base, redox, neither, or both. Well, I'm going to go to the redox first because we just looked at oxidation states, of which there was no change. So I'm going to say no change in oxidation state. As for acid-base, well, in acid-base, instead of changing and transferring electrons, we're changing and transferring electron pairs, depending on the theory we're looking at, protons. And when we go and look back at this reaction, we are donating protons, we're accepting protons. I'd say, yeah. Nitrogen is acting as a proton acceptor. H2O is acting as a donor. I mean, these are classic Lewis acid-base ideas. All right. Most nitride ions are 14N3, state the number of subatomic particles. Protons, nitrogen's atomic number 7, it's 7. Neutrons, 14 minus 7 is equal to 7. Electrons, we have a charge of 3 minus, which is produced by some amount of protons, 7 minus some blank amount of electrons, which is going to be 10. All right. Some nitride ions are 15N3 minus, some are 14N3 minus. What's the relationship? Well, these are called isotopes, which is different number of electrons. Nitride ion and magnesium ion are isoelectronic, meaning they have the same electron configuration. Determine giving a reason which has a greater ionic radius. Well, one of the best things to do when we're determining ionic radius or attraction is we could look at Z effective nuclear charge. In magnesium, we have 12 protons, and those outer electrons are only being shielded, especially in Mg2+, by 2 electrons. So this has a Z effective of 10 plus, which means those outer electrons are really, 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 really close to the nucleus because they are feeling 10 plus protons attracting them. When we do the same thing for our nitrogen, for nitrogen, which is 3 minus, we still have 7 protons, minus the inner electrons, which is only going to be 2, but that's a Z effective of 5 plus. They're feeling almost half the force of the nucleus. Therefore, they're going to be further out. So magnesium is going to be smaller, meaning nitrogen is going to be larger. So greater atomic radius, it's going to be the nitrite atom. So just 2 reasons why atoms are no longer regarded as indivisible units of matter. There's a million reasons. One, we have subatomic particles. Subatomic particles, which that gives us 3 reasons: protons, neutrons, electrons. We also have subatomic particles that are smaller. We've got quarks. Literally, you can name any of them, and that will explain it. We also can break an atom, also known as fission. There's like a million reasons they all work. All right. Last question. State the types of bonding in magnesium, oxygen, magnesium oxide, how the valence electrons produce these types of bonding. Magnesium. This is metallic. It's a metal. Metallic. Oxygen is covalent. Or diatomic oxygen. Magnesium oxide is ionic. So how the valence electrons produce these bonds? Well, they're delocalized around cations. In covalent, they are shared, and in ionic, they are transferred. Or another way of saying that is donated / accepted. There you go. That's the whole test. So do with that as you may, and hopefully you have a great day and this helped.